How do we define generally intelligent systems, and what does the path to something like AGI look like? Eric Jang is a roboticist who has been doing fascinating work since his time at Google Brain. His recent book, AI is Good for You, explains his perspective on what's needed to develop the types of systems that we might call AGI, and why he thinks AI progress is a fundamentally good thing for society. This conversation covers the different ingredients for an AGI system, how Eric thinks we'll get there from here, and his takes on positive and negative versions of our future with AI systems. This is the Gradient Podcast, and I am your host, Daniel Bashir. If you've been listening to the podcast for a while, or if you are new, you may or may not know that The Gradient is a project run by a few engineers and grad students. The podcast is, at the moment, a one-person effort. If you like what we're doing, it would mean a lot to us and to me if you'd consider supporting us by either writing a review wherever you're listening to this podcast or upgrading to a paid subscription on Substack. But now, without further ado, Eric Jang. Eric, it's been a little while since you've last been on the podcast, and I think you're actually the first person to make a repeat appearance, so welcome back, I suppose. And the last time you were on, Andre spoke to you about the work you were doing at Google Robotics. Since then, you've taken up a new position as a VP at 1X. I'd love to hear a little bit about just what you've been up to since the last time you were on.
Hey, Daniel. It's great to be back on the podcast, and it's a huge honor to be invited. So a few years have passed since I was last on this podcast, and I can share a little bit about what I've done since then. So at Google, I wrapped up a few big projects that culminated in some pretty impressive work on using language models to plan for manipulation policies, and we were able to do quite a lot of tasks in a Google Kitchen environment using the SACAN system. So I trained a lot of the low-level models that were able to do the actual manipulation tasks, and then we plugged this to the language model planner. After that, I was very convinced that the framework works, right? You just collect a bunch of data, you predict what the human teleoperator does, and then you just collect enough of it, and it'll just do it. And then if you want longer horizon stuff, you can plug this into reasoning models like language models. So I was quite convinced that this recipe will scale, and I think the last couple of years have sort of proven that out, that many of the manipulation labs have converged to this kind of language conditioned imitation learning framework. But also at the same time, I had realized that I think the hardware wasn't quite good enough to do all the tasks that we wanted to do. And I had so much conviction in this framework that I felt like at that time, the bottleneck was actually the hardware. So I wanted to move to something that was bimanual and not only just two arms, but able to really get into all the affordances that a human body could get into. So I started looking around for companies that were building humanoid robots, and I ended up meeting the founders of 1X, and they had such an impressive teleoperation and hardware system that I decided to join them. So that's kind of like what I was up to.
Yeah, that's really interesting. So I'd love to hear a little bit more about the kinds of robotic affordances you're thinking about now, how that differs from what you've been working on before at Google, maybe any of the particular challenges where you're trying to work on a robotic system that more faithfully looks like the way a human might interact with the world.
Sure, yeah. So the vast majority of robotic manipulation research today in academia is essentially a tabletop setup with some objects on the table and then a robotic arm bolted to the table. And the job of the arm is usually has like a parallel jaw gripper, which is just like a pair of chopsticks or a claw attached to the end of the arm. And it's supposed to pick up objects and put them down or open small drawers and things of that nature. There's also some work where you instead of bolting it to a table, you might bolt it to a heavy cart that can drive around. So you imagine it's just like a small car, and then you have an arm attached to it on the top. And these are what is known as a quasi-static setting, where the arm is basically assumed to be static, and then you can move the end effector or the claw around and pick things up. I think that in the next 2 or 3 years, there's going to be a really rapid shift away from this sort of setup where it's like a quasi static setting to either bimanual or even bimanual, but not exactly quasi static. And by not exactly quasi static, I mean that you can't really assume by default that the arm can go into sort of any configuration that the kinematics allows. Because, for example, if you're on some sort of legged system, it might actually throw the system out of balance if you're reaching too far out. So once you go to a form factor where you get away from the quasi static base, there's a lot more interesting problems to solve with coordinating the balancing and the locomotion and the manipulation together. And I think that's something that the robotics community hasn't really started to tackle. But because there is a clear sign of life on how to scale manipulation now and also how to scale locomotion, I think that's going to be a really interesting topic in the coming years on how to kind of merge these two together properly.
Interesting. And do you think that's just a problem of, I guess this might be getting into some things we'll go into more detail on in the book, but the embodiment aspect of this, do you feel like this is more at a very high level, something just like a reinforcement learning problem? Or do you have a different take on, I am a humanoid body learning to balance myself, learning to locomote and manipulate things in all the right ways? Like what are your intuitions on what that problem space looks like?
Yeah, so I suppose um, if we really zoom out, it's just a reinforcement learning problem in the sense that like anything that you use to do reinforcement learning could in principle be used to solve these problems as well. However, there's a kind of like practical challenge in the very near term, which is the following. Most robotic manipulation work is not really trained in reinforcement learning setups. It's often trained with just brute force data collection, behavior cloning, or some sort of imitation learning framework, and where you collect real data and then you train a model that does the task. And then a lot of locomotion work around, at least learned locomotion work, where you balance a robot, is often trained in simulation, like with Isaac Gym or something like that. And so not only are you combining reinforcement learning with imitation learning in this case as a challenge, but you're also actually combining simulation with real. So I suppose one kind of near-term challenge that the robotics community has to figure out is like, how do you combine this thing that's mostly sim trained and sim to real for locomotion and then real only data for imitation? There's probably some works out there that do it, but I think not a lot that really tries to push the scaling of like general manipulation with extremely robust legged locomotion. And you can't necessarily just like stitch them together like a Frankenstein monster because the many manipulation systems assume that you have a quasi-static manipulation workspace where you're like not moving the camera as you're like trying to move the end effector. And many locomotion policies assume that the set of disturbances that you add to the system are not like they might be like, you know, you're pushing the system, but you're not trying to actually reach a target with something that's attached to the robot. And so I think gluing these things together is going to be a little bit trickier than just training it in Isaac or just collecting more data in imitation learning setup.
Yeah, okay. I want to get more into some of the general questions about embodiment pretty soon. And maybe this is a good segue for us to begin talking a little bit about your recent book, AI is Good for You. So tell me a little bit about what got you started on writing this. What were your motivations in it?
Yeah, sure. So I actually started thinking about writing a book in 2019. Um, what I was seeing in the field at the time was that there's so many papers being published on techniques and methods and ways to learn a little bit better or ways to improve some benchmark. But then if I kind of sat back and thought, okay, like how do you put this all together into a system that's like a person, right? Like a real, you know, living, breathing person that has like goals and wants to, you know, do person things. It was just kind of like not clear to me how you actually glue these things together. Um, so you could take a paper that works on, I don't know, dynamic external memory, like some work coming out of DeepMind, but then how do you actually like, you know, make this connect to all the other methods out there? So I felt like there was a lot of stuff on like missing on how you glue things together. So what is a way to glue things together? Well, I guess in deep learning, the way you can glue things together is you just kind of slap some modules together, and then if you can make the thing end to end differentiable and you have some sort of objective that lets you tune the whole system end to end, then that is a way to merge modules together. So if you have like an external memory module and you have a planning module and you have a meta learning module and you have a perception module, each of these that came from different papers or whatever, and you want to build a bigger brain, maybe you could just slap these things kind of slipshod together and then make sure that the gradients flow between them nicely, and then you tune the thing end to end with some sort of objective. Well, what is that objective? Like, what is a sufficiently general objective that would let you glue all these things together? I became quite convinced that it's pretty hard to come up with a single task that really pushes all this. So you really need a very complex um, objective that gets things to really, exercise all these modules. And a very obvious one, just looking to nature, is just the problem of survival. So can an intelligent system just preserve its homeostasis, reproduce, maintain the state of the world internally to its body and locally externally around its body in the way that it wants to survive? And so I started thinking a lot about like artificial life at the time. And it's funny because I was like actually quite secretive about the fact that I was writing a book on AGI at the time, since I knew that if I told people I was writing a book on this, they would maybe say that it was like unprofessional to try to comment on this, or that we were so far away that any sort of book about it would just be more or less science fiction compared to like maybe something to be taken seriously by scientists. And I think that sentiment has changed in the last couple of years, where it's become much more mainstream. I think among at least among the machine learning community, that we are in the early stages of models that arguably have much more generality than much more generality, to the point where some of that generality is almost human level in some areas. So I think people are starting to like warm up to the idea that an AGI is possible within our lifetimes.
So, given what you've just said, I don't think I've ever popped the question on someone before about AGI timelines, and personally, I don't even love the question myself, but I feel like I kind of have to ask you about this. So, maybe before I ask you for a quote unquote AGI timeline, how do you define and think about AGI yourself?
Yeah. So in defining general intelligence, I think it's important to recognize that language is inherently fuzzy. And if you try to pin down an extremely precise definition of intelligence, for example, trying to bucket AGI into many different kinds of AGI, or coming up with some sort of scalar metric of how strong an AGI is, you end up in this very weird territory where you can come up with these very absurd definitions that kind of satisfy those absurd examples that satisfy those definitions, but are clearly not what we want. And this is I guess the classic example of like an adversarial input to some sort of classification function. So language is inherently fuzzy. I think if you could pin down a precise definition of AGI, you could just write down the program that is an AGI. So like there's also this kind of complexity argument to like how it's maybe not easy to write it down in a compact form. But just like loosely speaking, I think that an AGI is something that can do most of the things a human can do. And then, of course, there's also the question of like, what is the average human? So yeah, let's just say like, if you picked a random person from the human population today, an AGI would be able to do many of the intellectual tasks that they could do, potentially even physical as well. And I think also in machine learning, there's many ways to describe like what functions are. So for example, there are discriminative ways to refer to like distributions. You can say like this is in the distribution or not, and so we can have similar definitions of AGI. Like this thing is AGI like or not. And there's also other probabilistic ways to express this, like what is the compression ratio of an AGI, and then relative to the compression ratio of human. On AGI timelines, I feel like most people who give an AGI timeline are using motivated reasoning, which is that like they would like to see it happen within their lifetime, and also fast enough that they can enjoy the fruits of that labor. And I will confess and say that my AGI timelines are completely based on motivated reasoning as well. So in my book, I say 10 years. And this 10 years is kind of like accounting for the fact that things take 3 times as long as you want. So maybe like we'll try to shoot for a 10-year roadmap and then it takes 30 years because things take time. And it's completely motivated reasoning. But also, I should maybe say that, like, as pretty powerful agents, humans are the masters of their own destiny. So it's not like this is some external thing that just happens to you. Like, you can try to make it happen. So I hope that a 10-year timeline is, or at least a 10-year roadmap is possible. And then if it takes 3 times as long, I'll be pretty satisfied. That's kind of my timeline.
Let's break that down a little bit. So, the phrase intellectual or cognitive tasks is something that comes up a lot when people start to flesh out even loose definitions of what AGI could mean. What does intellectual task mean to you?
Without overthinking it too much, I suppose intellectual can mean just anything that has economic or creative value. So many jobs that involve using a computer, I would argue, are intellectual in the sense that they're processing information. Um, Many communication jobs are like human to human jobs are also, I think, intellectual because communication is a very important part of intelligence. Um, and then creative expression, I guess, like art, poetry. That's also intellectual to me.
Okay, that makes sense. So I think at this point, it kind of makes sense to ask you a little bit more on the timelines question. And you mentioned that in writing this book, you were thinking about how do we glue together, how do we stitch together things to build something that could conceivably be termed an AGI. So, coming from that perspective, do you feel like we have all of the ingredients right now at the moment in terms of potential algorithms, ideas, things that have been developed in order to build what you would think of as an AGI? Or do you think that there's something rather fundamental missing from the picture right now, besides the glue?
I think that if and when something like a human level AGI is achieved, and it's if it's not, I'm not certain it'll be achieved, but if that happens, I think people will look back and look at all the things that went into this system and be able to trace pretty clear parallels to ideas that have been proposed um, before 2023. So I think all the pieces will have like earlier precursors that clearly were, expressing very similar views. For example, like we need some sort of artificial life where things can evolve. That's been an idea since like the 1980s. We need deep neural nets. I think a lot of people believe this these days, and deep neural nets, today have been well developed. Um, People will say, "Oh, we need planning." I think probably the planning capabilities that go into the AGI will have precursors that have been already, like coming from papers whose ideas have been already suggested, but perhaps not implemented exactly the right way. Um, and so, yeah, I think most of the pieces are there. And I say this because when I look at papers today on proposing, many kinds of ideas for robotics or reinforcement learning or language modeling or whatever, I can kind of often find papers prior to that proposed similar ideas, but just maybe didn't execute with all the modern tools available with the latest paper. So I feel like most of AI research is essentially rediscovering old ideas, but improving them with more compute, better gradient flows, or smarter optimizers, or maybe just more data, like that kind of thing.
The rediscovering old ideas articulation is really interesting to me. And maybe before we get into how you think about the specific ingredients for AGI, you do include a component in your book on just the history of AI. And I think that's a lot of the broad strokes of that are things that many people are familiar with, the Dartmouth workshop, things like this. In your own research experience, as somebody who's worked mostly on robotics, for instance, and having developed a lot of really interesting ideas yourself, I'm curious how you reflect on what parts of the history of AI, both in its development, but then also in some of the ideas that have come out before you started getting into it. Like, what really sticks out to you? And I guess as an artifact of, doing your own research, maybe rediscovering ideas yourself, what feels like, I guess, to you as a researcher, just very personally, what are kind of the most important aspects of that history to you?
Sure. I should caveat this by saying that actually, as in terms of being a historian of AI research or knowing the literature in the field really well, I'm not that good at it. I haven't read enough papers to really be confident that I can like give a very accurate and fair characterization to the history of AI research. But I've read some papers, and I kind of know how the field evolved over the decades. So this is my noob answer. Um, I see a lot of parallels in robotics specifically around rediscovering old ideas. So, for example, the latest work on like diffusion policies for robotics is this idea that we can take the diffusion policies used to do denoising for images, like text condition image generation in stable diffusion. That idea has been recently applied to robotics from Sharon Song's lab in Colombia. And the idea is basically quite simple. Instead of denoising a image, you denoise a action. And this has connections to prior work in robotics pre-deep learning, where people would try to come up with function approximators that by construction were Lyapunov stable, which means that when trying to reach a target, it's not going to drift off course and veer off, and then you suddenly end up with the robot in a state where it's out of distribution of the training data. And so this idea of like staying on the manifold of your training data has been very old, pre-deep learning, and people are kind of rediscovering ideas like this. The recent work by Tony Zhao from Chelsea Finn's lab on Aloha and action transformers uses this idea called action chunking, but it's also an old idea, also known as like receding horizon control. So this idea of like you plan this trajectory and you execute the trajectory and you replan. And these ideas, I think, just keep on being rediscovered over and over again. So I see this kind of happen a lot. And I have no reason to suspect that as systems are scaling up, we won't just encounter exactly the same thing, where like an older idea that had the same kind of high level concept is just re-implemented in a way that suits the best function approximator of the time.
That makes a lot of sense to me. Yeah, and I think a lot of maybe in a lot of other episodes here too, we've seen different cases of what this looks like. I'd love to start diving into some more of the details about potential ingredients for AGI, how you think about these. And the first one, as a place to start, is artificial life that you mentioned. And I think this is a really interesting case, especially as we think about what does it take to develop like general skills of survival, of locomotion. One thing that kind of sticks out to me in this domain is I think back when Imbue was still called generally intelligent, one of the things they were beginning to develop was this very kind of general reinforcement learning environment where you sort of deposit an agent and you ask it to do a bunch of things that might involve navigating the physical world that are all essentially geared towards survival, and it kind of has to work with those affordances. I'd love to hear how you think about the importance of artificial life and that kind of system for a potential AGI.
Yeah, I haven't tried out the environment that generally intelligent slash imbue came up with. I forget, what was the name of the environment again?
I have actually totally forgotten by this point. I would need to look that up.
But it seems very well designed. I think they did have a very similar inspiration here, which is like you want things to emerge and you need a rich environment to make it emerge. And I haven't, and they also made some really nice engineering decisions, which is like optimizing for simulation throughput. So in certain environments like Habitat and Isaac Gym, it's been found that just optimizing the system for throughput often gives you a lot of um, immersion effects that you wouldn't be able to see in slower simulators. So I think that's a very important design decision that they made. And I haven't tried out the environment, so I can't actually comment on whether it has any engineering shortcomings. But I do know that like that was something that they prioritized, and that seems to be very valuable. Rendering is still a big challenge, I think, in many simulations, because if you have multiple agents, if you have a separate OpenGL pipeline, which is like a hardware accelerated rendering pipeline for each eye sensor, then in a sort of jungle environment with a lot of little critters, that's a lot of eyes to be rendering images for, and that would like slow down simulations quite a lot. So I think in order to really scale these things properly, so you have really rich multi-agent interactions, you have to go to something like like a Hyperion style render where all of the light transport in the scene is kind of done at once in batch for all the eyes in the scene. I think Isaac might also do something like this, but I'm not 100% sure.
Hmm. Another point that you make in your book is how in our physical reality, there's selection at different levels of information, and that we would need to create a world where life forms exist at many spatial and temporal scales, which is really interesting. I think that another conversation I've had recently that connects to this is one with Michael Levin, who's a biologist who really thinks about how intelligence can exist in this sort of substrate independent way, but then also at various levels, and where you have intelligence at the level of like individual cells, for instance. And I'm curious what your picture of that looks like. Does it maybe resonate with what Levin is saying? And also, when you think about the creation of a world with these types of life forms, like that, what you think a successful version of that looks like?
Yeah, I listened to your episode with Professor Levin, and I agree a lot with the multi-scale view on life. More broadly, I think there's this general philosophical question of what is the basic unit of life. In high school, we're taught that the cell is the basic unit of life, but that's probably not true because there are things like viruses that are not cells that clearly try, in some sense, to propagate their information. And and I think Richard Dawkins has written a book called The Selfish Gene about how even specific segments of genetic information within cells try to propagate themselves potentially at the expense of some of the bigger system, right? So there's clear examples of like this multi-scale thing happening. And if this happens for selfish genes, it also can hold true for selfish cells, selfish individuals, selfish cultures, and many different scales. And whatever is being selfish can be like that also implies that there is this bigger collective unit that itself is a form of self-organizing thing that competes with the selfish genes or selfish individuals to preserve life. So I think if you believe in selfish genes, it's sort of a logical induction step to kind of realize that there's many selfish scales, and then for each selfish scale there's the collective that's also a unit of life and could be selfish to the bigger thing above that. So yeah, in terms of how do you go about implementing this, I have not a great idea because I think nature tells us that if you implement things at a very subatomic level, like quarks and such, then you can do this. But it's probably not computationally feasible within our lifetimes to simulate reality at that scale. So then the real like question is how do you simplify this physical world so that you can still build something with this multi-scale emergent interactions? And we can kind of come up with a solution based on our computational constraints. So we know that we cannot simulate um, fluidics and cellular phenomena and squishy things in real time very fast because they just involve too many finite element methods and physics. Like in order to kind of simulate physics at that level of resolution, you just need to rely on actual physics to resolve those things. And if we're going to use digital computers, that's probably not going to work. So maybe there's things like cellular automata, and I think there's some cool work on from like Bert Chan on continuous time cellular automata that seem to have some rich emergent phenomena. But do you want to simulate the actual computer, the brain, using the physical substrate? So imagine you took a cellular automata and you tried to build a deep neural network out of that cellular automata. Well, it would be a terrible deep neural network. It probably wouldn't be anywhere close to state of the art on ImageNet or whatever, right? So again, even if you can simulate a physical world with some sort of approximation like cellular automata, there's still the challenge of like how do you build an extremely performant brain in that world? And so the most performant brains that we can build are deep neural networks trained with backpropagation with fairly simple units like ReLU and GeLU and things of that nature. Uh, and no one has ever figured out how to build these extremely performant networks with alternatives like liquid state machines or spiking neural networks or any kind of more physically plausible system. So there's a choice to be made there. And I think that if anything, deep learning has told us like you never should bet against deep learning. So if you want to go and try to make an artificial life program work, I think it's important to try to preserve the advances in the last decade of deep neural networks and find some way to bridge that with a abstraction of physics that's fast enough to simulate. And you kind of connect the deep neural networks to the agents in this world. But then you run into another technical problem here, which is if you have agents in the world, it's sort of fixing your notion of life, right? Like the notion of an agent is that it takes in observations and it emits actions, and in some ways that's your basic unit of life. You can have other physical phenomena in this world that don't emit actions. They just evolve according to the dynamics, and they don't make their own decisions via a deep neural network or anything like that. But then there's this problem of like how you bridge the non-living things that are just evolving according to the physical rules of the system and the things that are emitting control behaviors in the system. And so in robotics, people have always waved this away by just saying like there are parts of your system that you can control and parts of the system you can't control. So I guess these are some of the complex decisions that have to be made. And so if you kind of take all of this into account, what is a reasonable way to start, at least just get started? I think something like what DeepMind has done with games is a pretty good start. So you have a world that's not really physically realistic. It's based on game physics, and you have these agents that are also fixed in abstraction, but their decision making can be backed by a deep neural network, and you can run them separately from the physics of the world. Something like the environment that I remember now, Avalon. That's the name of the environment that General Intelligence came up with. Yes. So something like Avalon could also make sense as long as it's performant enough. Then I think maybe the kind of multi-scale emergence that you would hope would work is not at the cellular level. So you wouldn't want like things like cancer or selfish genes to emerge, but maybe you want to have more like population level emergence. So maybe you can have like individuals, and then they band together in tribes, and the tribes themselves can have selfish individuals, and then the tribes can band into a bigger collective, maybe like a town or something. And maybe you can try to build this sort of multi-scale life abstraction starting from the level of the simplified physics individual, and all of the emergence happens more in a social space rather than a physical substrate space. And I think that's maybe like the more computationally feasible thing in this century.
This is pretty interesting, and I think that it speaks to another thing that tends to come up, which is these ideas of, as you mentioned, collective social intelligence. And you do talk explicitly about social intelligence and what that might look like for agents in your book. One thing I'm curious about too is, are you open to a picture of an AGI system that looks something like this more collective? I feel like when we think about an AGI, it's always at the level of, I'm a human, there's this individual agent that is like a singular entity. And I'm curious if in writing this and thinking about these aspects of emergence, maybe has your view opened up to the idea that this is not like a single agent or something, but rather a collective?
I certainly subscribe to that view. I often make the mistake of thinking of it as like a single agent because of just my biases, but I also wholly believe that like the first AGIs will probably have a collective nature to them, or not probably, but like they could. One, there's already clear examples of this today. So, for example, the average person who tries to make money trading on the stock market loses money because they're trading against this collective agent known as the market, right? And the market is this collective, a bunch of participants, and together the market is extremely competent at trading, and so competent that the average person loses against the market. So you could argue it's like a superhuman. The market is basically this counterparty where most of the time when you transact with this counterparty, the prices move in the market's favor as opposed to your favor. And I have firsthand experience losing money on the markets for this.
Who doesn't?
Yeah, most people don't outsmart the market in the long run. So like that's a clear example of how a collective intelligence is better. And then also most corporations are way more economically productive than the average person, just because of the resources it's able to amass, and collective decision making often outperforms a single person as well. So again, I think those are very simple analogies of how like maybe an AGI could work. It's like it's sort of this emergent behavior that collectively when it interacts with singular individuals, appears as a very smart individual.
Yeah, and I think this idea of collectives and social behavior also comes up a little bit with the next component of AGI I was hoping to talk about with you, which is this aspect of human in the loop learning. And I think there are a lot of different ways to approach this conversation. Obviously, right now we have examples of a sort of human in the loop learning with RLHF and how that's getting transposed into systems. But I'd love to hear about how you think about this ingredient, how it fits in into your overall picture.
Sure. So I'm a big believer in imitation learning. I was a champion of this when I was at Google, and I think there's a sort of beauty to it, which is that it has to work if you scale it up. So imitation learning is this idea that you have a human tell you what the answer is, and then you just predict the answer based on what the information the human saw, and you're essentially swapping out the decision making process that the human brain did with a neural network. And if you collect enough samples of this, it should work in principle. So with human in the loop learning, there's this that's kind of like what I mean with scaling up these AI systems, is that you want AI systems to be able to vacuum as much human knowledge or human decision making as possible, because humans are very good at decision making generally. If you have a way to just continuously absorb information from human decision making, you can solve a lot of the exploration problems that is encountered in tabula rasa reinforcement learning, for instance. So, in building, let's say, an artificial life system, if you have a mechanism to inject human decision making into the system, then it provides you with a way to kind of scale up capability very, very quickly without having to search an enormously complex space. This has applications both on the kind of like artificial life, AGI timeline, but also on the just practical realities of deploying useful systems. So at 1X, we have these human in the loop systems we use to train the robots and improve from human demonstrations. And as you mentioned, RLHF is used to make language models and chatbots work when interacting with people, and they're absolutely necessary to make a useful product. Um, so human in the loop is needed just to make sure models are doing what we want, and you can fix the problems. But I also think that it's important for human in the loop um, to provide the necessary bits of information that you can use to kind of speed up the evolution process in a artificial life simulation.
How do you think about the whole scope of necessary bits of information for this? Because one thing you said earlier was making this jump from I have a system that kind of predicts the answers from a way a human does things in the real world, and jumping from that to, well, now we're replicating the decision making process. And I guess I see those as two things that can be rather distinct, right? You can make the right decision, but for the wrong reasons. And often we humans do that as well. And so I'm curious how you think about the am I developing a system that really does things in the right ways and for the right reasons, besides just mimicking answers?
Yeah, there's a lot of things you can mimic from people, and I think in the early days of machine learning, it was very simple, where it was just mimicking the answer, right? So you would present a human with an image of an object, and then they would recognize the object and pick one of 1,001 classes, and that would be the way that the human knowledge got stuffed into the network. But there's been a lot of creative ideas proposed in the last 10 years about ways to clone other kinds of human answers. So, for example, one thing that you can um, model from a human is not their answering ability, but their learning ability. So, if you show a human a sequence of events and the human is doing some learning process as adapting to that sequence, and the human is able to express their learning process, in textual form or something, then you can actually learn to predict the way a human learns, not the way a human answers. And you can extend this to other things. You could learn to predict the way a human thinks. And thoughts are not necessarily coupled directly to action, but like if there's a way to separate them out, you can try to predict maybe the human verbalizing their thoughts or something. And there's a cool paper, I think, from Jeff Clune's lab, where it's called thought cloning, where the human is actually articulating what they're thinking as they're doing stuff, and then you can predict this quantity as well. And so the space of human outputs is not just limited to actions and labels. It's quite broad. It could be how they react to things and how they understand the world. And as long as you have a way to record that, you can imbue very similar things onto virtual agents and models. And I feel like if you can make models think and react in ways that are very human like, it will actually improve the robustness of models dramatically because humans will then learn to trust them and they'll make the models much more predictable to humans as well.
I think another question slash challenge you brought up earlier also applies to this when it comes to the level of abstraction that we want to model these things. Because when you're modeling human decision making, you can think about the different scales at which things occur. And maybe it makes sense for us to break things down in a particular way. If I'm thinking about a decision I made and then I describe what happened in terms of maybe an emotion or maybe some physical causes, you can go really far back or you can get really deep when it comes to what your description of that looks like. And so, how do you think about forming intuitions about what's computationally feasible here and how it makes the most sense to implement something like that?
Yeah, that's a great point. So in the book, I have a chapter dedicated to the so-called neurobiological stack. And this chapter was very inspired by Robert Sapolsky's book Behave, because he also outlines his book in a very similar framing. So imagine you're a computer scientist debugging a human, and you're able to somehow set a breakpoint and freeze time. What you can see from a human decision making process is a large sequence of timescales with which events occur. So, like in the milliseconds prior to some action being taken through your motor pathways, there is the electrical state of your brain that is deciding to send neurotransmitters and electrical impulses to your muscles. And then you can kind of walk backwards in time to a larger time scale, which is like the hormones, and then a larger time scale, which is like the priming of the system through other memories and whatever leading up to that event. And you can walk this all the way back to the prenatal development process, the evolutionary lineage of that person, and then all the way to the Big Bang, or life, or the formation of life itself, right? So like the stack trace of causality is extremely long, and so yeah, when it comes to what is feasible to simulate, well, I guess our computers today probably can't simulate the microfluidics of hormones or maybe the synaptic spiking behavior in our brain. I guess there's this comes maybe a little bit contrarian because I think there's some computational neuroscientists who view that the spiking behavior is actually critical to cognition and spike timing is where it's all at. But I think the fact of the matter is that these systems haven't been merged properly with a deep learning framework yet. So until that happens, I am not so sure about the specific spiking neuron stuff. I actually did a bit of spiking neuron stuff when I was in college, and yeah, I found that it's kind of hard to make this stuff run in real time for the 100 billion neuron scale that humans have. So I think it just comes down to probably the abstraction people need to model at, just due to the limits of computation, is that you need to model language. I think that's probably the right abstraction here when it comes to inferring the kind of behavior of humans. Maybe there are other systems. So people are also increasingly finding that our organ systems actually do nervous system planning. So our spine does a lot of processing, and our kidneys and stomach do some nervous system processing as well in coordinating homeostasis. In designing agents that might be able to do these things, maybe we end up kind of expanding the deep neural net architectures to be more of a nervous system architecture rather than a V1 visual cortex type system. But I feel like in terms of just computational feasibility, if you're going to go and implement a nervous system with a stomach and some other organs, you probably want to keep the neural net architecture as close to a back propagated deep neural network as possible.
That makes a lot of sense. And before I dive into a specific part of your answer here, I want to ask one last thing on this whole section of human in the loop learning, where it was very interesting to me that you had a section on implementing loneliness. And I'm curious, just in developing an artificial life system or anything that could be thought of as an AGI, are there certain aspects of that implementation like loneliness that might come up in what a proper system should look like for you that you feel like, maybe aren't as obvious in terms of what people think should sort of go in the ingredients?
I haven't implemented such a system before, so and I know that like in this field, empiricism is sort of the true way to guide oneself on answering this question. So I can only give like a very like loose guess. Apologies for that. Um, Gait optimization is actually partially optimized by pain. So, for example, if you have like a injured muscle, you'll adapt your gait so that you don't put as much pressure on that muscle, and then as a result, you don't injure yourself and cause a very bad long term outcome of like being eaten by a predator or something, right? You like animals use pain as a way to actually locally optimize their long term outcomes. And so, if physical pain is a good signal for adapting your behavior to benefit yourself in the long term, then I think the same should be true for psychic pain as well, right? The pain of loneliness is a evolutionary adaptation so that people can pay attention to their social health and make sure that they're not ostracized from their tribe, so that they're not eaten by a predator or like caught off guard by a bad winter crop or something later on. So I think that as long as the environment demands a certain kind of social cooperation and sort of in the long term punishes agents that do not socially cooperate, it should be reasonable to expect that if you're able to train agents to kind of evolve intermediate reward mechanisms, that there will be a sort of reward predictor for agents that emerges that is very correlated to anticipating whether its social needs are met or not. And whether we can call this loneliness or not in practice is probably like a more of a philosophical discussion. But I think what would happen is that if you're implementing an A-life simulation where social cooperation is very beneficial for long-term outcomes, and you have a way to learn intermediate rewards or things that can kind of come up with local value functions, there will be some sort of salient neurons that correspond to I'm sorry, by salient neurons, I mean some units in this function approximator with a neural network would respond very strongly to predicting whether it's about to be socially rejected or not. And and then that would be kind of what we call the loneliness neuron or whatever. In the same way that there's like a sentiment neuron for language models.
I think that's a good way of explaining it because I can imagine somebody listening to this and hearing the idea of implementing loneliness and then worrying about, well, is there kind of an ethical thing here of you have a system that you've built that experiences something of negative valence, which of course assumes that it is capable of experiencing anything at all. And I think the picture you just painted is more like there's a simulation, this system has something that looks like a concept neuron, maybe like a loneliness neuron, and what it is for that thing to be lonely is for you and me to interpret what's going on in that system in a way that tracks with what loneliness looks like to us, but isn't necessarily implying that the system itself is having experience at all or that particular experience.
Yeah, I suppose I think there's certainly ethical questions to be like dealt with if AGIs are um, extremely powerful, and if you have a simulated agent that's saying like, "I'm lonely, please end my suffering," maybe you should like think about it more like a like yeah, the mechanistic view I just painted may not apply if like an agent is begging you to kill it. That that might be different.
That's fair. I want to use something you said a little bit earlier as a segue into our next section. So, you talked about language as potentially the right level of abstraction for simulating decision making and kind of breaking this down. And I think this kind of naturally leads into one of the really interesting sections here, which I know is based off of an essay you wrote a while ago called Asking for Generalization. And you start off in this bit by talking a little bit about the linguistic relativity hypothesis, that language is not only the way you and I communicate with each other like we are right now, but also the way we communicate with ourselves via thought. And I'm curious where you talk about it a little bit in the book, but it would be great to hear you explain a little bit where you are on linguistic relativity and this whole Worfian hypothesis.
Sure. Yeah. So I suppose the linguists have written quite a lot about this, and I only have like a sort of casual computer scientist approximate view of this hypothesis. So I'm not a deep linguist or philosopher on language. So yeah, where I currently am is that language is the way humans cast their entire understanding of the world. It's a sort of like compressed representation of the world that we use to communicate to ourselves and to each other. It's a lossy compressor in the sense that it doesn't describe everything about the world. And I think maybe a very salient way that comes up is that when people struggle to articulate what they mean, that's like an example of language not really capturing everything. But it's sort of the best we've got. And I believe that if language could be more compressed for the sort of use cases that humans require in communicating to ourselves or to each other, then it would become a little more compact, and we would discard words that weren't needed. And different cultures will like optimize their language to suit their ecological niche as well. For example, I think there's some tribes in the Amazon rainforest that have a lot of tokens allocated to brown colors, and then far fewer tokens allocated to blue colors. So, and that suits their lifestyle. Where I am is that I think the community has kind of recognized that language is a very good substrate for generalization. And as a result, if you can cast many prediction problems into the space of language, then you can benefit a lot from just pre-trained language models. And so it's a very good latent space to let me back up a little bit. In machine learning, often we want to come up with good representations so that when you try to train a downstream task on it, you benefit a lot from the structure of the representation. I think in the last couple of years, a lot of researchers have found that the structure of language is a very good representation to use because it understands a lot about the world, and many prediction problems can be derived from that space, as opposed to learning a completely new space from scratch. So I think we see a lot of papers trying to project their prediction problem into the space of language tokens, and then in that space reasoning about the model outputs. And that seems to be a very good strategy if you have enough compute capacity to kind of use the language model as your base representation.
If you have enough compute capacity seems really important here, because I think one aspect of our efficiency in doing things, to me, seems reliant on almost the idea that certain forms of complex thought or actions in the world are maybe not necessarily mediated by language. And this kind of came up with Ted Gibson, a linguist I spoke to. I think his episode should be out by the time this one is out. And he referenced some studies by Fedorenko, who works in a pretty similar lab, showing that this is kind of an open conclusion, but what they came to was that the language network in the human brain and then networks for other types of complex thought, so you might think musical, mathematical reasoning, are actually quite different. And they were able to confirm these with a lot of studies on participants. And I think what that kind of indicates to me is, yes, maybe if we're developing an AGI, a system that does things like locomotion or, anything physical or some kind of musical reasoning, then in principle, yes, you can mediate this kind of thing with language. But if you are really striving for efficiency and maybe even certain kinds of fluency, then it would almost seem to me like you have to move beyond language. If I kind of reflect on my own experience here, like I don't run by thinking, move one leg in front of the other, for instance, or when I was first learning to play an instrument, I did have to use language to be like, okay, like this finger goes here and all of these things. But I think as I attained fluency with that, the kind of inner voice in my head that was using language to figure out what do I do and to articulate that to myself kind of started to disappear. And so on that picture, which seems reasonable to me, then I'm curious how you think about the language as a substrate thing, because I think the given enough compute component seems important, but then in developing systems that either are human-like or efficient, it seems to me like a more direct version of doing certain things seems like a better way if possible.
There's a book, Principles of Neural Design, that also really inspired my own book in thinking about how I think about biological intelligence. And one of the principles of neural design is that there's this relentless optimization process to make things more and more efficient. So many animals in early like evolutionary history start out with repetitive units of general purpose components. For example, in a mouth, for like an early prehistoric jaw, it was like a bunch of molars of the same shape, and they're all kind of general purpose, and they do the job, and they're useful for a variety of things. And then over time, as the animal finds its niche, evolution will specialize the teeth in the jaw to make them more specialized and then less general. But then this also reduces energy requirements as well. So animals, because it saves energy to specialize, it's because you can offload the task of generalization into just like some specialized hardware. Many animals end up specializing their hardware, which is why we see like the Galapagos finches specialize as opposed to generalize. So yeah, there's this relentless evolutionary pressure in nature to conserve energy and specialize. And I think what we see is that like, small animals like bugs and lizards, they don't have language models, big language models running in their brains. They're not that general purpose. They've optimized their system to suit a specific niche and have very simpler circuits, if possible, to like solve their tasks. I think we'll see the same thing in digital intelligences, which is that if we find a way to do a task with less compute, with a less general representation, we will do it because it will save compute costs and it will allow us to serve models cheaper and smaller. And actually, in the case of 1x, we have to do some of these things because we just don't have enough compute to run a 7 billion parameter language model in real time. So there's definitely like a need for specialization. I suppose in the quest for what we call AGI, though, it's important to kind of like go for that and not succumb to the pressures of specialization too soon. And I suppose one of the mysteries to me is just like, why did evolution allow a general purpose brain like the human brain to sort of emerge? Like, why was this like? Why has the human lineage gone on for so long without extreme specialization on the brain side of things? That's kind of a mystery to me, but it happened, and maybe the case is that like in the sort of ecosystem of technology businesses, we'll have most companies doing specialization, and then like a few companies end up training models that are extremely general and get more and more general. That's kind of how I see the parallels in business evolution playing out.
Yeah, that's interesting to me. And I guess to your question about why the human brain evolved as it did to be particularly general, I guess our picture of what generality looks like in intelligence, of course, might not even be as general as things could get. And I guess the general intuitions here are, and you brought this up yourself in the book about how different organisms are adapted to their particular ecological niches. And it's that ecological niche and its demands that would drive the type of specialization you'd see in an organism. And so I'm curious here, when you ask that question, are you seeing maybe kind of a conflict between, well, humans have a particular ecological niche that is really, at least you might even describe it as not particularly niche, and so doesn't sort of afford those demands, but then also that question you just posed about why the human brain seems really general.
There's one evolutionary hypothesis, and I think this is just a hypothesis, but it's one I subscribe to, is that the generality is also kind of known as adaptability, right? So the ability to handle any situation that might arise extremely quickly. And one aspect of the environment that can adapt extremely quickly is the social dimension of like working with other people. Um, a a Galapagos finch can assume that the bugs will more or less stay the same shape throughout its lifetime, but a human dealing with a trading partner can cannot necessarily assume that the trading partner will behave exactly the same way day in and day out, right? Like, and as a result, the possibility for extremely rapidly changing social context might be the sort of niche that forces humans to be so general, is that the fact that other humans can change extremely rapidly and social dynamics can flip much faster than the evolutionary timescale. So it might be one of those things where like there's this snowball effect that happens where the generality of humans in a social context actually gives rise to more demands for even faster adaptation. For example, in a military context or a business context, or even just like interpersonal relationship stuff.
I'd like to move on to, I think, another kind of section here. And this is more about the idea of embodiment and real world robotics. And we've talked about different aspects of this kind of moving around it. And one of the important things you talk about in this section too is Moravec's paradox. And this is just kind of repeating what you said, that AI systems can solve complex cognitive tasks like playing chess, but then their sensory and motor skills really lag behind humans. And you provide an interesting insight here that it's really the tiny details of reality that text corpuses don't describe that give rise to Moravec's paradox. And I think that's rather important, especially along the lines of somebody like Stefan Harnad, who thinks a lot about this idea of sensory motor grounding as a way for humans to learn to do the right things with the right things by interacting with apples in the real world instead of eating apples and then like dying or not dying or getting sick or not getting sick and things like this. And so I'd love to hear you elaborate a little bit just on your feelings about the importance of embodiment in an AGI system.
Sure, yeah. That is a huge question these days, and I often see pretty interesting debates happening in academic circles about like, can we just get away with just language? Do we need multimodal? Do we need the multimodal thing to touch the world and then get feedback back? And I think um, prior to the sort of rapid progress in language models, I feel like the community was much more on the side of like, oh, of course we need embodiment. And then I think that belief has shrunk a bit in the recent years because people just see no end in sight to the capabilities of language models. So I find that quite interesting that like at least there's an interesting debate now on like what the limits of deep learning in the sort of internet scale data can do. I personally believe that embodiment and feedback from reality is important. So let me give the example of why. Um, Suppose you have a language model that is proposing the answer to something, and you have another language model whose job it is to verify the outputs somehow, or like check it for correctness, or make sure that the first language model hasn't made a mistake. And this is very practical importance because many labs are trying to figure out how to reduce hallucinations in language models, and a very obvious idea is to try to just take a language model and have it inspect another language model and then maybe check its work. Um, Interestingly enough, this idea doesn't really seem to work super well today, like with the current language models that we have available to us. There doesn't seem to be this automatic magical bootstrapping effect where you can just take a language model and then only using extra compute somehow search the space of outputs until another model is satisfied, and then you have a better answer than what the first language model could come up with on its first decoding pass. So imagine you took the second model and you then stacked on top of that a third model that was checking the outputs of the first two models, right? Like you can kind of take this idea inductively and try to just stack more and more models to verify each other's outputs. What seems to happen today with the models we have today is that they kind of seem to just degenerate into like models second guessing themselves. So for example, the first model might be really confident, the second model says it's wrong, the third model says the second model is wrong, and then a fourth model says the third model is also wrong. So who's actually right here? And it's very hard to actually check who's correct, and there doesn't seem to be an easy way to just really at the end of the day knowing whether the whole sequence of debate was valid or not. So there's a need in the language modeling space to kind of find some way to resolve the truth of like who is right, given some debate amongst a bunch of models. And so how do you get this answer? I think this requires feedback from reality. I don't really see another way around it unless you have like language models that make no logical reasoning mistakes. But then at that point you almost have like a perfect language model. So I feel like in order to make progress on the intellectual abilities of a language model, you do need feedback mechanisms from reality to tell you what is correct or not. So how do you get that feedback mechanism? Well, today people just have educated data labelers just do fact checking and rate answers as good or not, or harmful or not, or pleasant or not. But we kind of get also into this very fuzzy realm of like truth, which is like, is truth something that you just like, or is truth something that like is something that some people agree with? Is truth something that only everything is something that only everybody agrees with? And defining that is also very tricky. So I think you need to actually lift this into an even more grounded signal, which is sometimes truth is like what only a small thing. Sometimes truth can be something that only a small subset of people believe, and then it eventually grows into a larger subset. But at any given day, it's not like necessarily mainstream. So you need a mechanism for like the minority of beliefs to actually become resolved to be true. And I think that can only happen when you are actually interacting with reality, because reality doesn't care about majority minority beliefs. It's really just like is reality, and so you need a feedback mechanism to kind of ground truth.
Yeah, that's a really interesting picture. And I want to kind of dive into how you think about how embodiment is really fitting in here, because I think the picture you just painted to me is that the core system that has done a lot of the learning here is something that maybe looks like a language model in a very simplified case, for instance. And maybe in a robotic system, it's proposing different methods of achieving a certain goal. And it is that robotic system existing in the real world that can then execute these things and determine the truth of, is this a reliable way of doing the thing I am trying to do? And to describe that at a higher level, it's then just the language model is proposing all of the things we could potentially do. And then the embodiment part is just existing there as a verification mechanism. I think another way that people will think about the embodiment question, though, is also the embodiment as a core component of learning. I think that people talk a lot about this idea of process knowledge, for instance, when you think about, the intricacies of something like playing good piano or doing a lot of other actions in the world, working at a job that's relatively physical. Yes, you can describe these things, but then it's just the repeated motions of doing the thing in the real world that you don't articulate to yourself that really matter. I'm curious if what you just said there really reflects how you think about this, where the embodiment is more of a verification mechanism, or if you think maybe it's a little bit more a core component of the learning aspect than what you just said.
Great. Yeah, great question. So I like the way you put it, as embodiment as a verification mechanism. And in my earlier answer about like language models debating and not knowing what is true or not, I never really mentioned robotics. So let me just connect that bridge there. Suppose the task here is that the language model's like debating what action to take to open a door or something. So you want to open a door and you have a language model that's your policy, and it's debating with a verifier language model of like, how should I open this door? And the models can argue all day about it, but at the end of the day, like the only way to really know if it's correct or not is to just interact with reality and then verify the answer. And if you have a whole stack of models that like do debate and verification and solution proposal and whatever, at the end of the day there is a feedback signal that can kind of ground all of these models together, right? Like the verifier, if the verifier made an incorrect prediction, whether the door is open or not will sort of at least tell it indirectly whether it was wrong or not. And so verification is at the very least critical for grounding any kind of model that is making a prediction that is about the world that we live in. Because otherwise, like models can just kind of go off into this domain where like it's not grounded in reality. So at the very least, verification is important. And I guess that your second question is about the process learning, which is like, does it need to go further than just grounding with verification? I said verification first because I feel like that's a much easier position to defend. And then in terms of process knowledge, I think if you believe that language is a lossy compression of the world, to be clear, it's our best understanding of generalization in terms of how we communicate it to each other, because we cannot really do any kind of communicate. It's not easy for us to communicate in anything besides language for high level concepts. It's probably still lossy. Like as I said earlier, people can struggle to articulate certain things, and that's an example of where language is being lossy. And so if you want to learn something, maybe it's the case that the bits of information you need to learn the task, for example, maybe the bits of information that your spine needs to habituate to some particular motor pattern, or the bits of information that your muscles need to execute some particular violin motion, they just are not easily compressed into language, and so you have to get those bits somehow. And so I think process knowledge is also important for learning. But I think that's not to say that like you couldn't find some decoder that could map language into the information that your muscles and spine are learning to execute particular motor actions. It's just a hypothesis. I don't know the answer to that.
Yeah, that seems reasonable. And I guess a picture, like again, a kind of very high level description of a picture like this looks something like I guess you could call it bootstrapping, even if a very inefficient type of bootstrapping, where you do the majority of, I guess in the violin example again, I've learned the broad strokes of how to move fingers and things like that from mediation via language or something. But then I'm able to pick up some of the finer details through an embodiment mechanism. And so it's kind of that end to end learning maybe requires both aspects, but then you're able to do the quote unquote important basic work via a language mechanism or something.
I think, and this is just a hypothesis, I think what will probably happen is that if we want to build embodied systems that can really manipulate and understand the world, we'll find that there's many sources of nonverbal information that we need to collect in order to train these systems. And so probably the AGIs of the future will have like these verbal components as well as nonverbal components. And we will just have to accept that the nonverbal components are not things that you can describe easily, but you need to collect them anyway to like do the tasks. And it's probably possible that with sufficient nonverbal data, you can learn a mapping from nonverbal to verbal and then back, just with as any compression and prediction problem goes. So there's probably ways to like reduce the amount of data in one domain or the other, but probably there will be some kinds of data that are irreducible when it comes to the. If you learn some sort of projection from nonverbal data to verbal, it will probably lose some information, and if you need some of that lost information to do the task, then you have a performance hit.
Yeah, that seems kind of reasonable to me. I think a good final set of things to talk about would be your whole section on AGI and humanity. And I guess this is kind of projecting forward in the future. You paint a really optimistic picture throughout this book. And I guess I'd love to hear you maybe balance that a little bit. So, kind of projecting forward to a future with something that looks to you like an AGI system, what do successful and unsuccessful versions of that future look like to you?
Yeah, good question. So I'll answer the successful cases first because that's what I'm thought a little bit more about. The successful cases are a world of abundance, and I suppose it's kind of like how people today kind of look back on people living 100 years ago, and like those standards of living are sort of the poverty line today. Um, if things go well, AGI or not, technology will just kind of enable people to live extremely nice lives, and many more people will be able to live at a standard of living that today would seem um, luxurious. But from the perspective of people living 100 years from now, they would actually not consider their lives necessarily luxurious, but they will look at us and consider us in poverty. So it's humans have this remarkable ability to saturate their dopamine levels and expect that like what they're living in is just okay. So I think if things go well, people in the future will think things are okay, and then they'll look at us and think that, oh my god, like how did people in 2023 even like cope with life? Um, that's kind of at a very high level, like how I feel technology can benefit humanity. Um, and In terms of like specifically what AGI technology can do for us, I think it can help a lot with improving the social health of people. So, you know, improvements in agriculture and logistics make it so that most people living in developed nations never have to worry about food insecurity. Like we have plenty of food and calories, and almost anyone can buy any food they want occasionally, right? So um, that's like the sort of low level Maslowian needs have been taken care of. And I guess the most positive outcome of like AGI technology is that as we master the not only the physics of physical atoms, we also master the physics of like linguistic and social atoms, and that allows us to provide way more abundance in terms of like emotional connections and like well-adjusted people in society. Things of that nature would probably be useful with like intelligent agents. So then, okay, your other question was how can this go poorly? I think technology is like I view technology as a lever. So like it's not inherently good or bad. It's just like how is it used and how is it like who is it levering? So I suppose um, like any lever, the way that it could be exploited is that people use it to um, increase inequality. People use it uh, to I guess inflict much larger harms, whether it's like terrorist or state-sponsored military action. Like these kinds of things can can also technology like anything can be used to do this, um, and yeah, because this technology is very high leverage, you just like it can make bad people very productive, right? Like that's sort of the danger ahead with all technology in the past. I will say though that unlike many of my colleagues in academia, I am actually quite optimistic when it comes to AI technology as applied to the military, and I'm happy to go into that if you have follow up questions there. But I think actually AI in the military um, does make does actually dramatically reduce the loss of life and an unnecessary conflict as well.
Yeah, actually, I'm curious to hear your thoughts on this because I've also heard that opinion elsewhere. I think that the kind of obvious thing people worry about in this domain is, oh no, we're going to create killer drones or just things that could destroy many, many more people than we possibly could right now. I'm curious to hear your reasoning on that point.
Sure. So I think the biggest tragedies in military conflicts come from people making very difficult decisions under extreme fog of war with very little time and extremely high stakes and under a lot of pressure, right? I think Mark Andreessen basically wrote about this in his recent essay on like accelerationism. So, this is a point that does resonate a lot with me. So a lot of like unnecessary suffering is caused when people have to make these difficult choices in the fog of war. If you can expand the information um, that a military has access to, it allows them to avoid a lot of unnecessary suffering. So imagine you have a scenario where two sides are um, hostile towards each other and they want to engage in conflict, or there's some sort of escalation. If there was no fog of war, I would argue that it would dramatically reduce the amount of life lost because it would be very clear. Like you could use computer systems to anticipate with a very high a very high accuracy how much loss and how much gain you expect to have. It's actually kind of like playing AlphaGo, like playing with AlphaGo, right? If you had an AlphaGo for a military system and it could tell you your value function of like, you have a 99% chance of losing, you won't necessarily engage with the unnecessary loss of life that gets involved with the loss of life there. So yeah, I think that's like one way where technology can help reduce suffering. I mentioned the strategic part of it. I guess we can also address the more like tactical things like drones and guns on robot dogs and things like that. And again, I should clarify that like now that we're getting to like actual robots, like I'm only speaking on my own beliefs and not my employers. Many of my colleagues at 1X do not like the idea of having military use cases for robots, and we do not have any plans for that anytime soon, and I hope we don't. But that being said, um, I think the framing of like guns on robots is very dystopian and does draw out a lot of like emotional like negative valence. But the practical realities of like how the military wants to use these systems are a little bit different than how people are thinking about it. So, for example, suppose someone wants to mount a rifle on a robot dog. The goal is not to have the robot dog like go and hunt, the target, and then potentially make mistakes and things like that. That's actually the last thing that the military usually wants. What they see a robot dog as is like a movable tripod, and so like instead of having a soldier carry like a 200-pound gun, it would be much more ergonomic if they could just have the tripod move itself. Um, and I think some of the kind of realities of this are like that's more or less actually how they see it. And then with the drone stuff, it's like, um, what is the alternative? Like, would you rather have 10 people, risk their lives going into hostile territory? Would you rather have a human potentially make a mistake with a manual targeting system? I think like reframing it in terms of like, okay, if we don't do this, what is the alternative there? And then when you come to like those kind of decisions, I feel like um, a lot of technology is actually meant to prevent unnecessary loss of life rather than enact a very dystopian world where robots are just killing people at scale.
Yeah, I do like that picture more. The last thing I want to talk about here is you do comment a little bit towards the end of the book on AI beauty and AI's role in the creation of art. And I think that this is just a big rabbit hole we could get into. And so we don't have to go too deep into this, but there are a lot of different perspectives on this. One thing you talk about in the book is sort of the idea of books, media characters that are written for each individual person. And I think that in the context of like something like pedagogy, for instance, you can see this being really positive. But I think other people have criticized the idea of very individuated entertainment as potentially inducing something like a loss of culture. And those two things aren't necessarily entirely mutually exclusive, but there can be trade-offs since people only have finite time. And so I'm curious what some of, well, again, maybe I can rephrase or bring back my earlier question about in a world where AI systems are contributing something to art, what do positive, negative versions of this look like to you?
So I studied animation in college, and I have a great deal of passion for like animation, and computer animation is actually a field where it was a very good marriage of technology and art. Like for example, Pixar Studios' DNA is founded on this marriage between like high technology and high art. Um, I know artists today, like living artists today, who are at Pixar or who are very successful independent artists who actually use AI in their work. They're a little bit afraid to disclose this publicly because they know that there's a lot of like negative valence around this. But they use stable diffusion to refine their art or do stylistic work on top of their illustrations and things like that. So it's already today a multiplier to existing artists' workflows. I think that a potentially really nice outcome of AI technology being applied to art is that it deepens our understanding of how to make good stories. For example, you know, AI agents might have their own hopes and dreams. They might have their own tragedies, and these stories can provide truly um, true inspiration towards like new stories. So many humans, we're not fundamentally creative. We more or less like just interpolate between our own experiences and stories that we've read from other people's experiences, right? We just kind of mix and match them. And so, for example, Lion King is basically just a retelling of Hamlet and so on and so forth. And if you have more AI agents living out their own lives, you can end up with really interesting stories that probably most people could not dream of. And that will kind of usher in like a really interesting creative age where you have true like so maybe we call this like divine inspiration or something that's like truly separate from what humans can just dream up from themselves. I think that's like the upper ceiling of what could happen to art if we have AGI systems that have their own lives. So I guess yeah, the upper bound of AGI is that in terms of helping creativity is that we really vastly widen the Overton window of creativity of what things that we can mix together. I haven't thought of like I guess the worst possible case is like I don't know, complete human extinction or something. That would be like um, the sort of doomer case. But in terms of just like art creativity, um, the one negative outcome I can see is actually a reduction in the sort of biodiversity of creativity as a result of AI. So we actually have a precedent for this. Um, 3D animation has become very mainstream, And the success of studios like Pixar and Disney and Sony, like they've all sort of converged to this sort of 3D animation pipeline for a lot of their big budget movies. But this has also resulted in the death of 2D animation. So there's not any big budget 2D animation studios anymore, at least in the US, because technology created enough leverage on 3D that this was more economically efficient to make 3D movies. And another thing is that 3D movies test much better with like children's audiences and the sort of Disney's market than 2D animation. Um, and so we have lost 2D feature length films as an art form because of the economics and the sort of job market of 3D animation. One possible downside of AI art is that maybe it evolves us into new art forms that are like fresh and new, but it ends up killing off old ones like traditional 2D animation or 3D animation.
Yeah. Again, I guess as with all things, there's a lot of path dependence here. And so I think this kind of goes to a good final question. And this is just a little bit more about your commitments, thoughts as a researcher. I think going forward, a lot of the ways that we implement and develop systems is pretty path dependent, and the ways we ultimately use them are as well, as you've talked about multiple times. And so I'm just curious, as somebody who is working on robotic systems, for instance, how in your own research and kind of in your own area do you think about what you hope to do yourself to contribute to developing the type of future with AI systems that you think looks like a positive one?
Yeah. So at 1X, the company mission is to create a world of abundance with basically large supplies of labor. I think in a secular sense, the entire world is going through labor shortages, and for all the challenges of robotics, like there's many reasons not to go into robotics, but despite all this, the world is faced with labor shortages that no amount of SaaS software can fix. So someone needs to solve this problem, and it's one of those areas where if you don't do it, someone else might not do it, right? Like unlike another LLM rag startup, it's like not one of those things. It's not one of those things where if you don't do it, some other person in the next YC batch is going to do it. Like this is something where it's a very hard problem, and very few people are really trying to solve the problem um, in the general sense. So I think that my work at 1X is really focused on trying to take all the breakthroughs in machine learning in the last decade and scaling them up so that they are robust and that we can create more abundance in society where there's a lot of labor shortages. One example I'd like to kind of say here is like it's not really about taking our labor supply and then swapping it out with robots. It's more about like how can we create a world where there is 10x more labor. And I think people today don't have an answer. Like so people who are afraid of robots taking over the jobs and such, they don't want their own jobs replaced, but they also don't have an answer as to how we can 10x the volume of labor supply, right? And I think if you really frame the question in terms of like, in order to make the world better, you do need more labor. And so the labor pool actually needs to increase. And I guess short of just 10xing the world population, you do need to just make a bunch of robots to do this. So that's kind of the vision I have for how my career can fulfill this. And as to the path to AGI, this is not a direct way to AGI. It's more just like I want to build really, really good systems that can do tasks at a high level of success. And I think this will be a really good stepping stone towards actually building useful AGI systems through the mastery of things like deep learning.
I think that's a great picture and also a great place to end. So, Eric, I want to thank you, for the work you're doing and for writing this book and for also taking the time to talk about all this with me today.
Thanks, Daniel. I really appreciated the questions.
That's all I have for today. Thanks so much for listening to the episode. And if you like this, really the best thing you can do is to leave me a review and to share this episode with someone who might find it interesting. You can also subscribe to the podcast in your favorite podcast player, and if you want to keep up to date with the latest from The Gradient, to receive emails whenever we have new podcasts, newsletters, articles, then you can subscribe to us on Substack, where you'll get email notifications for everything.